Hello, my name is Dr. Justin Essery, and this is the first day of Paul 280 Research Methods at Wake Forest University. If you're watching online from some other university, that's great. However, I should note that a lot of the things we're going to talk about in this class are going to pertain in particular to the RStudio server that I've set up for this class. So while some of the lecture might be useful and interesting to you if you're learning how to use R, if you're learning how to use R on your own computer, maybe your professor has his or her own RStudio, that's fine. Some of the things, however, will not be as useful just because they don't apply to, for example, you probably don't have an account on my particular RStudio server. But we are going to learn how to log on to my particular RStudio server. We're also going to learn how to do some basic calculations and other things in R. So let's go ahead and get started. Alright, so the very first thing we need to do is log on to the RStudio server. So as you can see, this is located at rstudio.justinessery.com. That's my website. And for everyone in this class, you've already been assigned a login and password to access this server. Your login and password is your first, middle, and last initial in order. So in my case, that would be JEE, first, middle, and last initial. That's both your login and your password just to start. Now, obviously, you don't want to leave that as your password for the long run because you don't want other people looking at your homeworks or messing with your tests or whatever. So you can and should change your password right away. And I've included a little link here about how you can change it. So if you click on this link, you should, or type it into your browser, I suppose, you can find some instructions on how to change your password, and you should do that as soon as you successfully log on. So let's go ahead and log on to RStudio and take a look at what that should look like. Okay, so this is what the RStudio server login page looks like. You can see I've got rstudio.justinessery.com right here in the upper in the bar. This auth sign in will be added automatically once you type that in. It's kind of a blank looking page, but there's a place to put in your username, which in my case isjessery, and your password. So once you do that, and you can click to stay signed in if you want. It doesn't really matter. You just have to do this every time. If you don't click stay signed in, click sign in, and something should appear. In fact, you may not have this week 1 script open yet, so probably what will appear will look a little something like this. Maybe you'll have your files listed here. This is the RStudio environment, which uses the R statistical software package that we'll be using in this class. And there are 4 windows, 4 panes inside of this window, I should say, that will appear whenever you open RStudio. One of them is not open right now because I just closed it. That's the source window. But if I open a new R script, you'll see that's the source window. This is essentially just a text file, like a sketchpad, like Notepad. And if I come in here and I type something in like, this is my first R program, and maybe the first thing I would do is clear out the memory space, nothing happens. It is as though I have written down these commands and these comments and whatever just on a piece of paper, like in a notepad. They won't actually be, nothing will happen in R, in the actual R statistical program, until I run these commands. And when I do, they'll appear down here in the console. Console is where the actual R statistical software program lives. And so if, for example, I were to highlight these 2 lines and click run, then they would appear down here, and R will have done something. In fact, what it should have done is cleared out the memory space, which there isn't anything in the memory, so basically it did nothing. But it could have done something. Another thing, just to show something that might have happened if I do a simple math calculation, I can come over here and click run again, or I can just click Control Enter, and it'll automatically go down into the R console window, and you can see in this case something did happen. It calculated the sum 2 plus 2, which we can verify equals 4. So when you're doing your homeworks, when you're doing class assignments, when you're doing whatever it is you need to be doing in R, the best thing to do is to write your commands, write the things you'd like to do up here in the source window, and then come down here whenever you're ready to run those commands, and you can either use the run button or control enter. You can actually even copy and paste if you really want to do that, and then run them in R to get answers, to get results, statistical results or calculator results or whatever it is you're doing. So that's these two windows. And just to point out real quick, your RStudio window might look different than this because these are all customizable. So if you go to Tools and Global Options, you can actually change the appearance. You can change what the colors look like. I like a white text on a dark background because I think it stands out better, but you can set it to whatever you want. You can also change which panes are in which locations. So I have the source at the top right, the console in the top left. Yours might be somewhere else. There is no right answer for how to do this correctly. There's just 4 panes. You can arrange them the way you like. If you'd like to arrange them in the way I have them, you can see how my particular code window is set right here. You can stop the video and look at that. And if you really like my particular background, tomorrow night bright I think is my settings, but you can none of this is going to change your results. It's just how it looks. Okay, so there are 2 windows left. The window down here in the bottom left, you can see there's some tabs at the top. There are a number of things that can appear in this window. What's in here now is files. These are files that are in your home folder. You can see I'm in my home folder right now. Your home folder is going to be accessible with just the squiggle, which is the key above the tab. You shift and then the little key above the tab has the squiggle in it. The actual name of it is going to be /home/ and then your name. So you can store in your home directory homework files, script files, data files for your own projects, whatever it is you want to do. You have write access and read access in your own home directory. There's also a directory for the entire class that we all share. And that directory is called Pol280. That's the name of the class. So if you click on these 3 dots up here in the go-to directory, you can see if I type the squiggle and then OK, I get to my home. I was already there. But if I type /Pol280, just that, and then OK, now I'm in the Pol280 folder. And you can see there's tons and tons of files in this folder pertaining to things we're going to do in this class. Now you can read the things in this folder, but you can't write to this folder. You cannot save your homeworks in this folder. You cannot save your data in this folder. You cannot change the scripts or the data that I've put in here. And that's to protect the class, is to make sure someone doesn't come in here and accidentally delete all our stuff. So when you're going to save something, we'll talk about how to save things in a minute, you're going to want to make sure you're not in the Pol280 folder anymore. You want to save it in your home folder. And in your home folder, you can save whatever you like. The other things will appear in this window too. So if you plot something, a plot will appear in this window. If you ask for help on a particular command, so whenever you're confused about a command, and I'll just, since we already typed the RM command, if you type $RM, you'll see a help file will come up. And this help file describes what the command is, what you type into the command. It tells you what it actually does. RM is used to remove objects. And if you scroll down, it'll give you some examples of how these things work. And so if you ask for help, and then the command to get help, that help will appear in this window. And there's a viewer as well, which I think shows data views, I think. And then finally, this last window up here to the left, top left, is the environment. That shows what is in R's memory right now. And right now, as you can tell, the environment is empty. R does not know anything. I've not given it anything to remember. But when you load data sets, when you store results or store vectors or matrices or any kind of data object or function or something, it's going to appear in this environment window. And that's to let you know that R knows about it and R can use it. So when you type the remove list equals ls command up here, just like I've typed it, that environment should become blank because what's happening is everything's being removed. There's also a history window here. You can see this is like a long history of stuff I've done before. This will show you all the different commands you've typed during this R session. Sometimes this is valuable. I don't find this particularly valuable, but I will point out that if you just type the up command, if you just hit the up arrow in the console, the previous commands that you've entered will appear. And I actually do use that quite a bit. That's basically stored in the history, but you don't need to click on the history tab in order to access that. You can just hit up in the console window and you'll get that. All right, so that's a brief introduction to the RStudio environment. You can see I've also got in the slideshow here that's uploaded with this particular lecture, a sort of reminder of like what's in all these windows and why are they there and what do they do. All right, so now that you've had a look at this environment, let's start doing stuff. All right, so the first thing we need to do is go ahead and open a script file that I've prepared with commands and things for us to use during this session of R, or during the session of class. So what you should do is first in the Files tab, navigate to the Pol 280 folder, and then click on week1.r, which is the file containing the commands we need. So if we open up, let's see, we open up RStudio right here. What we need to do is we need to click on Files, because that's where we want to find the files that we need. Click on here, navigate to Pol 280, and in fact I'm already there in this case. Scroll down and click on week1.r, and then the week1.r script with all the commands we're going to use today should appear right in the top of this script. So you should be seeing week1.r right in the top there. And just to get everyone started, if you take these first 4 lines right here and run them, that's going to accomplish a few things. First, the first line is going to clear the workspace, which get rid of anything that happens to be in memory. The second line is going to load a library that is helpful for loading data sets. So this line here allows us to open Stata datasets and SAS datasets and SPSS datasets from programs that are not R, essentially. And then the third line, which is probably the most important for right now, is to set the working directory to the Pol 280 folder. So your working directory is where R is going to look for its various files. It's where R is going to look for data, for example. It's also where R is going to try to save something if you just click Save. So if you type git wd, and then parentheses, it will show you where R is looking for files and folders right now. So right now, it's looking in the Pol 280 folder. That's where it will look for, you know, for example, if we save something, or if it's going to save it there. If we try to open a file, it's going to try to open it from there. That's where we want to be. The initial place you were was probably your home. So if you set wd, I think you just do squiggle, and then do get wd. Yeah, this is now we're in my home folder, which would be appropriate if we were we were using data that came from my home file, essentially. But we're not. We're going to use data that we're all sharing, and so we want to set the working directory to Pol 280. Pol 280 should be in quotation marks. It should be / Pol 280. And then just get wd to verify that we're in the right folder. So now we're ready to actually get started with running some real R commands, loading in data and making plots and doing some analysis, simple analysis. All right, so let's talk about some basic principles or rules when you're entering code in R. The first thing to know is that in R, commands are case sensitive. What that means is there's a big difference between the command, let's say, lowercase mean for mean, and the command uppercase m and then lowercase ean. So going back to RStudio for a moment here, there's a difference between this and this. And they may or may not, depending on how R is being set up, they may or may not work in the same way. So you can see some things down here where we're doing plotting. We'll talk about plot command later. Lowercase POLT is different than uppercase POLT. So the first thing you need to know about R is that its commands are case sensitive, and that's something important to remember when you're typing in those commands. And when you get an error, that's one thing that you should check. Commands can be separated with a carrier return. What does that mean? Well, that means that, for example, at the end of this line right here, at the end of these lines we typed before, we ended the command and told R to execute the command by essentially pushing return, right? So if I were to try to clear the memory again, Hitting return is what separates the commands from this command from the next command and tells R to go ahead and execute that command. So all these lines are separated with returns, and it's the return that sort of gets things going. Third, anything following a pound sign or the hashtag sign, if you're more Twitter oriented, I suppose, is a comment that's R. It's ignored by R. It's not there for R to read. It's there for humans to read, the people doing the programming. So again, going back to RStudio here, you can see there are lots of comments, right? So for example, to save a file to your directory, there's a little create a vector of dates. These are some commands talking about clearing the workspace. These are explaining what these commands do. These comments are there and they're grayed out in my particular scheme so that you, the reader, the student, or the analyst, or whoever, can know what these commands are there for. So the first line is there to clear the workspace. The second line is there to load a package which opens data sets. The third line is there to set the working directory, and here's some other information about other places you can set your working directory, and so on, right? It's there to be human readable. It's not there to be readable by the machine. R, for example, if I type this command into R, line 6, nothing happens. And that is not a mistake. Nothing happens precisely because R ignores anything that's followed by a command sign. So that's just treated as a comment. Finally, numbers can be part of object names, but they cannot be the first character. So going back to RStudio here, I can call something temp.1, and I'll just store the number 5 in there. Okay, so temp.1 is the number 5, right? The little right or left pointing arrow means that 5 is being stored in temp.1. That's fine. That's a normal name. R will treat that just fine. But if I were to call that 1.temp, it would yell at me. I would get an error. Unfortunately, the errors for R are not always super helpful. So you can see it's telling you there's an unexpected symbol in 1.temp. That is true. R does not expect to see numbers as the first symbol in an object name, but it won't just come out and tell you you can't have a number as the first thing in an object name. You just have to know that. So you'll get an error. It won't let you do it, but you need to know why. And the reason why is because numbers can be part of object names, but not the first character. So one thing we can do, now that we know some basic things about R, is we can use R as a calculator. The TI 84 or 85 or maybe 86 plus, I think they have now, that you used in high school. They're still using it for the SATs and things like that. But there's really not much need to use it in a statistics class because anything it can do, R can do much better. And that includes very simple things like addition, subtraction, multiplication, division, exponents, and logarithms, and other things. Well, if you don't remember what the logarithm is, by the way, we'll talk about that in just a few minutes. But for now, just if you do know what they are, R will do them. Parentheses, just like on your calculator, group commands. So if you want the certain things to be done first, putting them in parentheses makes R do them first. So here's a little example problem. What is 2 to the 12th power? It's definitely one of these three things, 24, 4096, or 144. Well, that's very easy to find out in R. So all we need to do is, here we go. We need to do 2 to the, what was it, 2 to the 4th power? 2 to the 12th power. So 2 to the 12th power is 2 caret 12, 4096. So 2 to the 12th power is 4096, and we know that because the caret command is the exponent command. Now, you might be wondering, how can I do like cube roots or fourth roots or something like that? Well, there is this squirt for square root command, but the easier way to do it and the more flexible way to do it, in my opinion, is just to do fractional roots. So, for example, if you want the third root of 2, 2 to the 1/3 power is 1.259921, and you can verify that that's approximately the cube root of 2 by cubing it, and you get 2. So all these things that R can do, all the things your calculator can do, R can do, and you can see 4096, going back to our original slide here, was answer B. So we got that right. That's the right one. Here's an example that draws on the syllabus for this class. So again, those of you watching who aren't actually part of Paul 280 may or may not be able to figure this out unless you happen to look up my syllabus. Suppose a student in this class got the following grades. 2 homeworks, an 85% on the first, a 78% on the second. On the 2 exams, they got a 79% on the first and a 94% on the second. And they got 100% on the final project. What is this student's final grade? So what I would recommend is stop the video for a second, see if you can do this problem in R, and then come back, and once you figured it out, see if you got the right answer, and then we'll do it together. Okay, to answer this question, we need to calculate a weighted average. So the syllabus says that essentially the homeworks, the exams, and the project each get 25% of the weight. So each exam gets 25%, the project gets 25%, and the average of the homeworks gets 25%. So the person got an 85 on the first homework and a 78 on the second homework, and we want that to be averaged, and so we're going to use order of operations and divide that by 2 to get the average, the sum divided by 2. And then we're going to put that in parentheses because we want that to be multiplied by 0.25 because it's 25% of the grade. And you can't just put it next to the parentheses. You actually have to use a, what do you call it, an asterisk to indicate that you want it to be multiplied. Then I got a 79 on one exam, that gets 25% of the grade. And I get a 94 on one exam, and that gets 25% of the grade. And finally, I get 100% on the final project, and that gets 25% of the grade. So average of the homeworks is 25, the exam is 25, the second exam is 25, and the project is 25. So the average grade is an 88.625. And if we go back to our original slideshow here, you can see that is actually one of the options that's available to you as one of the guesses. So we got it right. So just to finish this off, I guess, R can be used as a calculator. Anything you can do on a calculator, you can do in R, but of course you can do a lot more. So let's talk about what more you can do. So when you're working in R, for various reasons, including the fact that you have homeworks you need to save and projects you need to work on, you're often going to load data sets, modify data sets, you're going to do analysis on data sets, and then you're going to want to keep a record of the things you've done during that session. You're going to need to turn that into me or turn that into some other professor for some other project, or whatever it is you're working on, you're going to need to have a record of that. And so when you're analyzing data or programming in R, there are 2 basic rules you should follow when you're thinking about saving. First, whenever you're working with data, don't change the original data set. Now, that doesn't mean you can't actually do things to that data set. You can add variables, you can modify variables, you can take subsets of cases, whatever you need to do. But you always want to leave the original data set as it was intact. And the reason for that is if you modify that original data set and you make a mistake, or you decide you want more of the original variables or more of the original cases, if you change the original data set and you don't have another copy somewhere, you're kind of out of luck. So whenever you do work, you want to leave the original data intact and then update the data with a new name or something, and then save that revised version of the data. That's going to get you out of a lot of trouble. Everyone makes mistakes, even the most advanced programmers and analysts make mistakes. That can get you out of a lot of mistakes. Another thing you want to do is you want to be able to remember what you've done. You don't want to forget, how did I get this result? Where did this result come from? What did I do to get this result? Why is this right? Why is this wrong? You want to have a written record of everything you've done. And so the best idea is if you're thinking about RStudio, so if I go back to RStudio here, you don't want to just type random things like into the console and then just have this disjointed record where, like, you can see my own record here. I've got duplications, I've got mistakes, I've got gaps that are weird. This is a mess, right? What you want is a nice, organized text file This is actually a .r file, but it's just a text file. .r just says it's something R can use, but any text file R can open. And it's nice and organized, and it has comments, and I can tell exactly what I've done and exactly how I got the results I got. And if I just rerun this script from the beginning, I should get the same results over again. So going back to my slideshow here, write your input code into a script, not into the console. And if you're going to make a major revision to your script, you might want to save multiple versions. There have been times I've done something, I've said, oh, this code's wrong, I delete it. And then I later realized, actually, that code was right. I should still have it. And so if you're deleting stuff and just leaving it out, you're lost it forever. But if you save multiple versions of a code script, then and you decide you want something else you already done, you can go to that earlier version, pull it out again. So what this requires is that you know how to write files into various places in R. So as we already discussed earlier in the script, you can type git wd and then parentheses to obtain the working directory that you're already in. And this is important because whatever the working directory you're in is where anything you do is going to be saved. So to change the working directory, the syntax looks like setwd and then in quotation marks wherever you are. And actually, so Poly 395 was a course I used to teach, and just scratch that out. Pol 280 / and in quotation marks would be the current course. That's how you would set your working directory to like access files we would be using in class, like data files and stuff. But you can't save anything there. You're not allowed to write onto that particular place because it's designed to be used by everyone, and only administrators like me can write to it. So you need to change your working directory before you save to somewhere where you can save things, right? So don't try to save it in Pol 280. Save it in your working directory. So if you want to save your R script, right, which is the list of commands that you've done, not data, just the script, you can click File Save As, which brings up this little dialog, and then you can navigate to your home folder and then save your thing in your home folder. So save your script rather in your home folder. So if I go to my RStudio here, you can see I've got week1.r. Let's say I wanted to save this to my home folder. Now if I just click File, Save, nothing's going to happen because I can't write to this particular directory. But if I click Save As, then I can change. You can see here I'm in Pol 280. I can change to my home directory, and my home directory is squiggle. You can actually type a longer thing if you want, but squiggle works. And so that'll get you into your home directory where you can save it as anything you want. So if I save it as like, oh, some random script.r, and then I click save, it appears that nothing happens, but if I navigate to my home directory in the files tab, you can see some random script.r is there. I have saved some random script.r into my home directory. And then if I'm going to download that into my sort of laptop or my desktop, wherever I'm working, I can check next to that and then do more and export, and then I can download it to my folder. And you can see it's actually, you can't see it, but it just appeared on my desktop. And now I can do whatever I want with it. I can turn it into a professor. I can save it in my hard drive, whatever I want. These directories are secure. They'll be secure at least for the they'll be saved over the time period that you're in this class if you're taking my class at Wake Forest. But they won't outlast that most likely. And so and you also can't directly turn things in from this particular screen, right? You have to download it to your desktop and then upload that script to Sakai or the course learning management system that we use to turn it in that way. So that's how you can get stuff, at least script files, out of R. And in fact, the same thing you can do the same thing with data. We'll learn a little bit more about this later, but I believe if you go into environment and that's to import, yeah, you can actually click save and then save your workspace. So if you need to save a data set, you can save your workspace. But again, you won't be able to save to Pol 280. You'll have to change to your home directory first and then save it there. So you can save your workspace, which includes all your data and everything you're working on in there. Okay, so that's how to save script files in R. Now let's talk about a little bit of at least a little bit real. It's real. Plotting and data analysis. All right, so now we're going to create a relatively simple plot out of a relatively simple data set. What I'm going to do is plot two very short vectors against one another. One is just a series of dates, and one is a series of total carbon emissions emitted by human activity in the world. And so the first vector is a vector of years. These are dates. A vector is just a concatenated series of numbers, and you can see here this C right here, that stands for concatenate. And this tells R in the, as you can see, there's C here, and then there's the parentheses, right? So this is the first part of the command, this is the last part of the command. This tells R to basically attach these numbers together as a vector. So 1800, 1850, 1900, 1950, and 2000 are the 5 dates that for which we have data. And carbon is a different vector. It has the total carbon emissions. This is obviously not in tons. This is probably in, I think this is in thousands of tons or millions of tons. I'd have to double check that. Again, we're concatenating together a bunch of values. 8 is the emission level in 1800. 54 is the emission level in 1850. 534 is the emission level in 1900. 1630 is the emission level in 1950. 6611 is the emission level in 2000, which is almost 20 years ago. So what we're going to do is we're going to plot these two vectors that are both concatenated together with the C or concatenate command using the plot function. And there are multiple ways to do this. This is just one particular way. You put in the plot command, and then you put in whatever variable you want on the x-axis, in this case is year, whatever variable you want on the y-axis, which in this case is carbon, and then you could stop right there. This is an additional option that tells R to use specific kind of point when it's going to plot the points. In this case, this corresponds to a filled point, like that. The default is actually a hollow point, so if you put in just this with no PCH specified, it'll use hollow dots. And just to remind you once again, if you use question mark and then the command name, you'll get lots of information about what's in this command, so you can find out more about, for example, where to enter each variable and what these options possibilities are and so on. Okay. Oh, and one more thing. So this concatenate command comes up a lot. It's going to come up again, for example, when we subset data, and it comes up quite a few times, I would say constantly in R. So whenever you need to stick a bunch of things together, very often you're going to want to use the concatenate command to basically attach those things together in the form of a vector. So if we go to RStudio, you can see I've already entered this information into R. This is part of your week 1 script. And if I just run these two commands, you can see that carbon and year now appear in the environment. And that's because those things have been stored in the environment. Now we have a little tiny data set. And if I type carbon into console, it'll put out that vector of 5 elements. And if I type year, it'll put out that vector of 5 elements. And then if I plot these things together, I get a plot. Now this plot doesn't look super great. It's a little bit squished, so I can maybe mess with the proportions a bit. I can shrink it down. I can maybe expand this a bit to make it a little more squarish. And you can see that what's happened to carbon emissions over time is they've gone up exponentially. As our economy has grown, we've gotten more technologies for extracting energy from fossil fuels. We've basically burned more stuff, and more of that product of that stuff, CO2, has been emitted into the atmosphere. The PCH equals 16 makes it points instead of, if I were to leave off the PCH 16, you'd get hollow dots. That's the default. You can change this to other things. There's actually a big list somewhere you can find online of what all these things are. That seems to be hollow dots with an X through them. That's 13. 11, oh, is the Star of David. 10 is, little crosshairs or whatever. I liked 16. It's hollow, but you don't have to do that. That's just customization. That does bring up an important point. There are dozens and dozens and dozens of ways to customize plots in R. Not just changing the points type, but also what's on the axis labels, how the axes are labeled, the direction in which the dates and the labels are shown. All kinds of things can be customized. If you don't put in those customizations, R will make choices for you. It'll just basically do whatever its default is. And if you want to know more about those customizations, you can always type question mark to find out more about what all these options are. And you can see there's actually ... because there's so many options it doesn't even want to list them all in the usage. And if you scroll down here, you can see all these different options. And in fact, there are sub options. Like if you click on graphical parameters, you'll see all these different parameters you can set. We'll learn about more of the common one, most of the common ones as part of this course. One we're going to learn about right away. We go back to plots here. What if I want to make this a line instead of dots? Well, if I specify type equals L, I will connect basically each point with a line instead of with dots. And then if I use the points command, I can actually reestablish the points on top of the line. The points doesn't just draw points on a new plot, it actually puts points on top of a plot that already exists. So you can see now I've got this little graph here that has points on top of the line. I should also mention that there's more than one way to do these plots. And so you can see that the help command here, x is the first argument, that's whatever variables on the x-axis, y is in the second argument, y is whatever variables on the y-axis. So we put year on the x-axis right here, we put carbon on the y-axis right there. That's perfectly fine, it'll work. It's not the only way to do it, so just keep that in your head for a moment before we'll come back to that in just a second. I entered these carbon and year things just as sort of random vectors. Most data come as variables or vectors in a data frame, which is basically a big sort of Excel type spreadsheet kind of thing with a bunch of variables in it. I could create a data frame called fossil fuel that, so you can see here's the data now. It's got 5 observations, 5 years, 2 variables, year and carbon. And what I did to create this data frame was use the data.frame command. And so if you do question mark data.frame, you can see this creates data frames. Collections, tightly coupled collections of variables which share many of the properties of matrices. Right? It's basically a spreadsheet with data in it, like an Excel spreadsheet. I can store that in using this left arrow command. The arrow sort of says whatever's on the right hand side of the arrow, put it into an object on the left hand side. That object is called fossil fuel. So now I have a data frame called fossil fuel. And if I get rid of those old vectors, now the only place that those data are located, those year and carbon vectors, is inside the data frame object called fossil fuel. In fact, if I type capital year, now nothing happens because I got rid of year, right? I removed it from the data space. That's where the remove command comes in. I removed 2 things, year and carbon. They're still there, but they're inside of a data frame now. If I actually type lowercase year, it also nothing happens because I need to tell it where to look. I need to tell it to look inside of the fossil fuel data frame. So if I do fossil fuel $, and then it actually brings up a little menu because it knows what's in there. If I just type year, now I get the years. Notice that this is case sensitive. If I were to type capital year, it would null means there's nothing in there called capital year. It's called lowercase year. That's where the years are located. If you use the view command, I just run this, it brings up a little Excel type spreadsheet inside of R that gives you a sense of what's in this data set. All the variables appear in the columns and all the entries appear in the rows. All the observations appear in the rows. It's exactly or very much like an Excel spreadsheet. There are limits to how many things View can show. I believe it can only show like 1,000 observations at once. So with very large data sets, it won't show you the whole thing. It'll show you part of it. So I'm going to close that now. Now I'm going to show you this plot again, and I'm going to change the commands a little bit. I'm going to get the same answer that I got before. You may recall that's the answer I got. But I'm going to use a little bit of a different style. So I could, if I wanted to, I could do the exact same thing I did before. Now this is not going to work anymore because I don't have objects called year and carbon anymore. But what I could do, right, I could say I want to do fossil fuel $year and fossil fuel $carbon. So that's telling it to look at the fossil fuel year and fossil fuel carbon variables that are both in the fossil fuel data set. If I do that, I do get, in fact, the same plot. So that could work. I could also do this sort of formula type format. And if I do this, you'll see actually I specified PCH equals 16. So what I get is the points. I could have changed that to type equals L and gotten the line. And you'll notice this syntax is a little different than the syntax I used before. Instead of doing x comma y, now I do y and then squiggle, which is not your home directory. It means it's sort of like equal sign. It's making sure R knows this is a formula. And then year on the right hand side. So it's saying predict carbon with the y-axis using year on the x-axis. And look in the fossil fuel data set, so comma data equals fossil fuel. That tells it to look in the fossil fuel data set for those variables. And then PCH16 just sets the point type to a particular type. This raises some important points that I want to stop and talk about right now. There are lots of ways, typically, to do things correctly in R. There are many ways to essentially come to the same conclusion. Some might be more complicated, some might be simpler, some might just be more comfortable for certain people to understand. They're all equally valid as long as they produce the same answer. Of course, there are an infinite number of wrong ways to do it, but they're often a non-unitary set of ways to correctly do it. And so in this case, all these different ways I did this all basically gave me the same answer. I personally prefer the formula format because I'm just used to thinking in formulas. So if I were to type this in on my own, I would probably do it that way. But in your homework assignments and whatnot, you know, I wouldn't necessarily require you to do it that way unless the problem specifically asked you to do it. So I can put all these to summarize what we've done. I can create a common data frame out of these things, remove the other variables. I can then view that to show an Excel spreadsheet type view. I can do some various kinds of plots. I can do line plots. I can do point plots. And you can see that my notes here, I'm using the formula format. So it's y squiggle x and then plot around that and then whatever options I put in there. That's the format I tend to use the most. I think it's personally the most convenient format, but you could have done plot x and then y and then whatever options gotten the same thing. Although you do need to remember if the variables are inside of a data frame, so if they're in like a fossil fuel data frame, you need, when you use this format, you need to tell R to look in that data frame. So you might have to do something like plot fossil fuel fossil fuel $, X would be year, right? And then the same thing for Y, and then whatever options you had, fossil fuel $, carbon. You might need to do, in fact, you will need to do that if the data are located in a data frame like fossil fuel to tell it where to look. Okay, let's move on. Okay, so obviously entering in data one by one in a long vector is not going to work. If you've got like 5,000 observations of something, you know, a bunch of country data by year over 50 years or something, you're not going to type them in R one by one. So generally speaking, what you're going to do is you're going to load data in from some file that you've already gotten from somewhere. And you can save data into a file from R. But more often what you're going to be is loading in data that's already been assembled from somewhere else, from a government, from some experiment, whatever. You can even enter in data in Excel and then save it and then load it in R. That's going to be the much more common thing you're going to want to do. So you can do that. You can read in data from R. There are lots of data types that R can understand. The easiest is so-called fixed format data. Fixed format data is essentially data where the information is distinguished by variable in a file by carrier returns and some sort of separator. So if you think about what this file would actually look like, imagine an Excel file where you've got rows and you've got columns. Except we don't actually have rows and columns in a text file. We do have carrier returns, which separate lines, essentially. And then we might have a tab or a comma or something that separates values into columns. So you might have data that sort of looks like this, 15, 14, comma, 12, 21, comma, 13, 42. And then if we're going to move on to the next, this is one observation in one line or one row. And then when we move on to the next row, we do a carrier return, right? And then that moves us on to the next one, and we might have 4, 3, 5. Those are the observations for the next, the values for the next observation. Hit carrier return, and we get 91, 72, 63, whatever. This is what the fixed format actually looks like. It's basically a text file where the values, the variables, this is like variable number, or we'll call this variable A, variable B, variable C, are separated by commas. In this case, would be a comma separated variable file. .csv is often what the end of that file looks like. That's one kind of fixed format data where the observations are separated by returns and the variables are separated by commas. There are other kinds of fixed format data. So sometimes instead of having commas in here, there'll be tabs instead. So you hit literally tab between each one. That would be a tab separated file. Tab separated files don't have their own special extension. Don't ask me why. Sometimes they're just saved as regular txt files. There are other kinds of fixed format too, although I would say that comma separated and tab separated are the most common, and I would say probably comma separated is by far the most common. Of course, with a little bit of work, R will also read in other kinds of files. It'll read in .xls or even .xlsx files, which are Excel files. It'll read in Stata data files. .dta will actually be reading in quite a few Stata data files in this class. These generally require some other packages to read in. So for the .dta, you need the foreign library in order to read those in. We actually typed that at the beginning of our script so we could read in data files. XLSX, I forget exactly what package you need. There's a special package to read those in. The easiest way to do this in R is to save your data when you're collecting it or getting it somewhere as a comma separated variable file, because R knows how to read those in very easily. Sometimes these are actually saved as .tab, which is actually short for table, not necessarily tab separated, but .tab files. And the example we're going to do right now uses a .tab file, and I believe it's actually a tab separated tab file. Yes, so we're going to load in this human rights data set. This is discussed in the Monaghan book that is assigned for this class, which hopefully you've read. You'll want to make sure that your RStudio is pointed at the working directory that we're working in. And you want to load in data that's saved in a tab separated format that's saved in our Pol 280 folder. So make sure you're pointed at the working directory Pol 280 folder that's shared for the class. And then we're going to create this data frame object called human rights. Remember, this left pointing arrow basically puts whatever's on the right hand side and stores it in an object that's named according to the left hand side. The command we're using to do this is called read.table. Read.table allows us to read in fixed format data that's either comma separated or tab separated, whatever. You just have to give it the file name. You can see we give it the file name. Note that the file name is in quotation marks. We have to put the quotation marks in so that it knows that's the file name. There's this sep argument. This is the separator, and essentially what separates the columns from each other. And the quotation /t is computer language for a tab. So this is a tab separated file. If you were to use a comma, if this was a comma separated file, you could use sep equals comma. That would work. You could also use, as a shortcut for that, you could use read.csv, and then the file name, whatever it is, .csv, and then whether there's a header. You could use read.csv that way. If this were a CSV file, you can also use the read.table and specify that the separator is a tab. Finally, this last argument, header.true, tells R that the first line in the file is a line of variable names. So instead of there actually being the first line is the first observation, the first line is actually just a vector of strings, of text strings, that tells it what each column's name is supposed to be. So if you open up your RStudio here we go. Oh, and I need to open up my, I need to get to my week 1. So here we go, week 1. Here's the line right here where I'm reading in this data. And you can see the data now appears up here in the data environment window, indicating that I have 158 observations of 8 variables in this data. So now the data is loaded. If this were a CSV file, I could have loaded in some sort of CSV. So if I look at Paul 280 here, actually I should note here, you have to make sure before you load this data that we're in the Paul 280 folder. If I had been in the home, so now I'm, wait a minute. So if I was in my home folder and I had tried to load that command, nothing would happen. It would give me an error because the data is not in my home folder. If you actually go to my home folder here, this humanrights.tab is not there. Ergo, it's going to say I can't find that. But if I go to Paul 280, where the classes data is stored, you can see it is there. H for human rights. It's right there, humanrights.tab. And then the command does work once I set working directory to Paul 280. Then the command does work and it loads in perfectly well. You can see we've got some other CSV files here. There's fred.csv, fresh.data CSV, or fresh_data CSV. Just to show you how that CSV command would work, although we're not using it right now. If I were to do this, that would load in the Fred data set. It's looks like 100,000 observations of 2 variables. And you can see they're big X and little x, whatever those may be. I also could have used read.table and specified that the, I would have had to specify that the separator is a column, or a comma rather, and header equals true. And you can see actually the same thing happened. In other words, those two are the same commands. But we're going to focus on the human rights tab separated data set right now, so I'm going to just remove this Fred thing, show you how that worked. That's kind of nice. Let's see what's in this human rights data set. So one way of looking at that is I can just do head human rights. That'll give me the first 6 observations of the human rights data set. And what you can see is this data set is composed of single observations for a bunch of different countries. This is cross-sectional data, which means one point in time, just looking at countries, or whatever units we have, in this case countries. And we've got a bunch of different variables that we've observed for these countries. We've got the democracy score, which is that's compiled by the Polity Project. It rates countries on essentially how democratic they are, with the highest score, most democratic, being 10, the lowest being 0. We've got some information about the military, some information about their gross national product in categories. We've got some information about their log population. And the population is some big number, so we take the logarithm of that number to make the bigger numbers smaller. And then we've got information about whether there's a civil war or an interstate war going on at this time in that country. So in Afghanistan, there is a civil war happening. There's no interstate war happening at this particular point in time. I could have also done view human rights, which brings up this little spreadsheet that allows me to show at least the first 1,000 entries, and there are only 158 entries, so I can actually look at all of them. That'll give me a sense of what all is in this data set. I can look at the various values here. All right, so we've loaded the data set. We've shown a couple different ways of loading this data set. Now let's actually do some analysis with this data set. All right, so to review what we just saw with viewing the attributes of the data, actually one thing you can do, although I don't recommend it, is if you just type human rights into the console, it'll actually spit out the entire data set, which generally, I guess that could be useful in some cases, but it's going to omit, it's only going to show you the first bunch of rows. And often with a data set with many observations and many variables, this kind of doesn't help that much, but you can do it. It can be done. More helpful is to maybe look at the first few observations using this head command. You can also look at what variables are in the data set by typing names human rights. So if I go in here and type names human rights, it'll give me a list of all the different variable names for the variables in this data set, like country, which is the country name, democ, which is the democracy score, GNP cats, which is the GNP score as a series of categories, and so on. I can do the view human rights to see the spreadsheet. Now what I want to do is actually do a little bit of analysis on this data set. For example, I might want to summarize the data set to get a sense of what the average value is for each of the variables. And if I just go into RStudio right here, and if I just type summary human rights, it'll give me a bunch of summary statistics for each of the variables in this data set. So this is a summary of the, let's see, the GNP cats variable. So there are 66 countries in this data set that have a gross national product of fewer than $1,000 per capita per year. This is obviously a per capita data set, or per capita measure. 21 have GNPs between $1,000 and $1999 dollars per capita per year. 16 have GNPs between $2,000 and $29.99. 8 have between $3,000 and $39.99 per person per year, and 41 countries have GNPs per capita of $4,000 or more per year. Actually, it's greater than 4,000. That's weird because it says greater than 4,000, but $39.99 here, so this really ought to be greater than or equal to 4,000, but whatever. But $4,000 or more per year. There are 41 countries in that category, and 6 are missing. 6 are NA. So I didn't get a mean for GNP categories because this is a categorical variable, and so it just gives me counts of each category. For the democracy score, it's a number between 0 and 10, and so for each country. So I get a mean. For example, the average democracy score in this data set is 5.3, which is basically the middle of the scale. You can see the minimum and the first quartile, which is to say the number for which 25% of the observations are less than or equal to that number, are both 0. And the third quartile and the maximum are both 10. And that kind of makes sense because what we're seeing here is that most countries are either sort of on one side of the scale or on the other. There are relatively few countries in the middle. The median, which is basically the number of the country with an equal number of countries having a bigger and a smaller democracy score than it, is 7, which is a little in the middle toward the higher end. And the mean is 5, and so what I get a sense is this is probably a bimodal data set or a bimodal variable where there's an equal number of countries roughly on each side of the middle. So a lot of 0s and a lot of 10s, maybe some 9s, maybe some 1s. We'll have to look into that a little more carefully later. The country summary is not very helpful. It's just telling you there's one observation for each country. The mean value of civil war is 0.096, which means that 9.6% of the countries are experiencing civil war. They're 1s. The rest are 0s. 0 means not experiencing a civil war. 1 means experiencing a civil war. And then for interstate war, you can see 0.0256 is the mean, which means that about 2.6% of countries are experiencing interstate war. Again, 0 means not experiencing, 1 means experiencing. You may be wondering how I know this. Like, how do I know that 0 is not civil war and 1 is civil war? Generally speaking, what you'd read is a code book that tells you more about this data. And the Monaghan book has a little more information about what's in this data set, but usually data sets come with like a PDF code book that describes exactly what's in them. In this case, the variables are so common that if you've just been around and done a lot of analysis, you can take a pretty good guess about what things are going to be. So typically, Civil War is categorized as 0 for no and 1 for yes. You do need to be careful that sometimes they use weird categories, but in this case, I think we can safely assume that that's what the categories are. And if we want to know more, we can check out the Monaghan book. Okay, let's see. So if you want a descriptive statistic on a single variable, if you don't want summaries on the entire data set, you can pull a single variable out of a data set using this $, which we saw briefly before, but now it's a good time to just call that out. So if you type basically the name of the data set and then a $, and then the name of the variable, that tells R to pull this particular variable out of this particular data set. So if I want to do a summary, for example, of the democracy score, let's go in here. If I want to do a summary of the democracy score, I can't just type summary democ because it says I don't know where democ is. And you might say, well, wait a minute. You can see, it's right there. Right? It's in this data set. You ought to know that. But R will not understand where that is unless you tell it where to look. And it's not. There's nothing in the environment that's actually called democ, right? There's something called human rights. Inside of human rights, there's something called democ, right? It's right there. So what we want to do is we want to tell R, I want to look inside the human rights data set at the democ variable, and then it'll give me summary statistics for those. So there are 31 missing values. The minimum is 0. The maximum is 10. The first quartile, 25th percentile is 0. The third quartile, 75th percentile is 0, and so on. That can be helpful if you've got a data set with a million variables, not a million, but 100 variables, and you're really only interested in 1 or 2 of them. Okay, let's do a couple of practice questions to make sure that you understand what's going on with R, and you can actually answer some basic summary questions. So I've got a couple of check questions here. The first one is the data sets from the year 1993. Was Albania experiencing a civil war, which means civil war equals 1, right, in 1993? And the second one is, what is the average value of the log population, which is LPOP, of countries in this data set? So take a few minutes, see if you can figure this out, pause the video, get your answers, and then we'll come back and discuss those answers. All right, so our 2 questions are, first, was Albania experiencing a civil war in 1993? Well, there are lots of ways to answer this. There are almost always many ways, correct ways to answer something in R. One very simple way in this case would just be to type head human rights, because Albania is the first or the second observation, so we can just go in, look at this particular row, and see that civil war is 0. So ergo, no civil war in this case. Another way to have done this would have been to do something like look at the country variable, figure out that the second one is Albania, and then come in and type human rights, and I want the second row and all the columns of this particular data set. And you can see now I've pulled out row number 2, civil war is 0. How did I know that the second observation was Albania? Well, I went into the country variable and I saw the second one was Albania. I also could have gone view human rights and then seen, aha, there's Albania right there, civil war 0. All of those would have been equally valid ways to figure out the answer. The second question was, if I recall correctly, what is the average value of log population among countries in this data set? Well, so what I need to do here, again, there are multiple correct ways of doing it. I could do a summary, of human rights, $, and then LPOP. And the mean value is 15.66. That's one way to do it. There are other ways. One thing you might be asking is, I don't understand what a log population is. We don't usually think in terms of logarithms. What number does that actually correspond to in actual numbers? Well, the log is the anti-exponential function, and the exponential function is the anti-log function. So if I type exponential of 15.66, I get 6,324,870 is the average log population. Now compare that to the max, which is 20.89. If I were to type exp 20.89, that's a much larger number. And you can see how the logarithm works in this case. It's making the really big numbers. The difference between 15.66 and 20.89 is only about 5, right? It's a little more than 5. The difference between 6 million and 1.2 billion is a lot more than 5. And so it's tending to make the bigger numbers sort of scrunch down closer to each other, and the small numbers stay closer to their same range. It's a way, a convenient. There are some nice properties about it, but one thing it does well is it sort of scales numbers that have big, long, tails where like there are a few huge observations and then a lot more observations that are more moderate. Logging the variable tends to put those numbers on a more comparable scale. So the bigger ones will always be bigger on a log scale if they're bigger on a non-log scale. But the log it keeps the order the same, but it makes the gaps a little smaller at the high end, or actually it makes them a lot smaller at the high end. So that's why we might log variables. Okay, so going back to our spreadsheet, or our slideshow here. Was Albania experiencing a civil war? Well, the answer was no, right? 0. And the average log population is, so this is a no, and the log population was 15.66. All right, so here's another check question. The human rights data set contains data about the democracy level of each state, which is this DEMOC score on a 0 to 10 scale. 0 is the least democratic, and then the log population of each state. Create a plot predicting the democracy level of the state using the state's log population. And what that means is you want to create a plot where log population is on the x-axis, and then democ is on the y-axis, because we want to explain democracy using log population, and by convention the predicting variable is on the x-axis and the predicted variable is on the y-axis. And then you want to answer the question, is there an apparent relationship between democracy level and log population? So construct that plot. We discussed line and scatter plots a little bit ago. Go ahead and construct an appropriate plot and then answer that question, and then check to see once you're done that. Pause the video. Once you've done that, turn the video back on and we'll check the answer together. All right, so here's another check question. The human rights data set contains data about the democracy level of each state, which is this DEMOC score on a 0 to 10 scale. 0 is the least democratic, and then the log population of each state. Create a plot predicting the democracy level of the state using the state's log population. And what that means is you want to create a plot where log population is on the x-axis, and then democ is on the y-axis, because we want to explain democracy using log population, and by convention the predicting variable is on the x-axis and the predicted variable is on the y-axis. And then you want to answer the question, is there an apparent relationship between democracy level and log population? So construct that plot. We discussed line and scatter plots a little bit ago. Go ahead and construct an appropriate plot and then answer that question, and then check to see once you're done that. Pause the video. Once you've done that, turn the video back on and we'll check the answer together. Okay, so we want to know if democracy is related to log population with some kind of plot. So what I'm going to do is use a plot. I'm going to plot the y variable is democracy score. I'm going to use the squiggle for the formula. The x-axis value is log population. And if I just stop there, it's going to say, I don't know what those variables mean. I actually have to tell it where to find them. And there are two ways I can do that. I can either do the human rights $, whoops, human rights $, in front of both. And I'll get that plot, which is the correct plot. Or I can just type comma data equals human rights And you can see actually the same thing happens. And the labels change a little bit. It includes the $ thing in the first one. It drops it in the second one. But they're the same plot. So now the question is there an apparent relationship here? Well, I think I would have to say probably not. If I were to draw a line, you don't want to simply connect the dots, but if you were to draw a line that sort of described what was going on in this data set, I'd probably just draw a flat line at about 5, which basically says if I know something about the log population, no matter what, my best guess about democracy score is still in the middle, about 5. Now, that wouldn't have been true if, for example, there had been some sort of linear relationship, right? So maybe the small countries tend to be non-democratic, the big countries tend to be democratic, and we'd have like a sloped line. That wouldn't be true if there was a negatively sloped line. It wouldn't be true if there was a U-shaped line, maybe. Maybe both the little countries and the big countries tend to be democratic, the middling countries tend to be less democratic. But we don't see any of that. All I see is there's a bunch of countries, they have a bunch of populations, and that population doesn't really tell me anything about the democracy score. I can't learn anything about the democracy score from the log population. So probably I'd have to say the answer is no. There's no apparent relationship between log population and democracy level in this data set. All right, so often what we want to do is we want to select out certain kinds of data. So maybe only the democracies or the high democracy score countries, maybe only countries experiencing a civil war, maybe certain groups of countries. And when we need to subset data, we need to basically be able to identify data as having certain characteristics, like, has democracy score less than some value, greater than some value, whatever. So we frequently use these Boolean or logical operators in order to construct these tests for whether certain variables have certain characteristics or not. So many of these you've probably seen before: less than or equal to, greater than or equal to. Those are pretty obvious ones. And R is going to, if you say like A is less than B, well, now it works. If you say A is less than B, R is going to evaluate that as either true if A is less than B, right? Or false if A is less than B. If A is not less than B. So if A is equal to B, or if B is less than A. True and false are specific values in R that have a particular meaning. The capitalization does matter. It needs to be all capital true, all capital false for R to understand that these are true or false. You can also, actually that's probably not the best thing to do. You can also write this as just capital T or capital F, but you cannot do this, you cannot do this, and you cannot do this. Those will not be understood, F. So capital T-U-R-E, capital F-A-L-S-E, or capital T and F. That's what R understands. So it evaluates whatever statement you put in with these comparators, and then it says it's either true or false. You'll notice we also have equal to, and it's a double equals. That's because this means the same thing as this in R's language. So R treats a single equal sign as an assignment. If you want to test whether A is equal to B, you have to put in the double equal. Then it will know to do a test. There's not equal, which is it's just exclamation point and then equals. And then there's and or. And or are evaluated according to Boolean rules as well. So if we say something like A and B, that will only be categorized as true if A is true and B is true, right? So A and B is true is, this is, for example, classified as false if A is false, or if B is false, or if they're both false. They both must be true in order for this to be equal to true, in order for this to be true. Or is different, or is inclusive or, which means if A is true, or B is true, or they're both true, then this statement is true. So if A can be false, B is true, it's true. A can be true and B is false, true. If they're both true, statement's true, but only if A and B are both false is this OR rated as false. So you may have been exposed to this maybe in a philosophy class, maybe in some other programming class, but these commands get used a lot in R, and they get used, for example, when we want to subset data. So suppose we want to only examine countries in our data set that have a democracy score between 6 and 10. You can use the subset command to do that. You say I want to subset the human rights data set, and I want to subset it on the basis of the democracy score being greater than 5, which means not including 5, right? 5.1, 5.2, yes. 5, 4.9, no. And we would store this in some object name. I called it dem.rights in this case. You can also, so actually before we get into that, let's just try that in RStudio. So you can see I've actually got this command here as line 41. And I've created a new data set called dem.rights. It's right here. dem.rights. There's 73 observations of 8 variables, whereas our original data set, human rights, had 158 observations of 8 variables. And a couple ways you can know this worked. One way is if I do a plot. So I previously did a plot of democracy on LPOP on the human rights data set. If I now do dem.rights, oh, I spelled it wrong. You'll see now only countries with democracy scores of 6 and above are included, whereas previously more were included, right, all the way down to 0. So I did subset that correctly. I pulled out only the most democratic data. If I wish to do so, I can also only select certain variables out of the data set. So I can say I want the human rights data set, but I want to ignore the information about civil war. I want to ignore the information about interstate war. I just want the country name, the democracy score, and GNP cats. And I can do that with the select command. Select tells it which variables to pull out. So I go back into R here. Here's this command I've already prepared for you, dem.wealth. You can see dem.wealth has 3 variables. It has 158 observations. It didn't subset it all, but instead of 8 variables, it pulled out 3 variables, right? There are 158 observations of 3 variables instead of 8. So if I do a names on dem.wealth, you can see there are only 3 names because I only pulled out 3 variables. You can combine these 2 commands. I can subset and select at the same time if I want. That's totally okay. And I can even combine the subset command to do multiple different options. So suppose for some reason I wanted to create a data set that only had civil war countries and were experiencing democracies. I could say, and I'm going to put this in parentheses, I want countries with democracy greater than 5 and civ underscore war equal 1. Oh, I typed asterisk instead of and. There we go. You can see there are only 4 observations in this data set because there are only 4 observations that are high democracy score and are also experiencing a civil war. And in fact, if I just type dem civ rights, you'll see what they were. Colombia had a democracy score of 9 and a civil war score of 1. India had a democracy score of 8 and a civil war score of 1. The Philippines and Turkey had democracy scores of 8 and 10. Both were experiencing a civil war. So you can combine different sort of combinations of things together in order to subset on multiple criteria at once. In this case, we're subsetting on both democracy is 5 and civil war equals 1. Okay, so go back to this. This is maybe something you wouldn't use a lot, but if you want to select all variables except a particular variable, you can use the minus sign after the select command. So you can see I've got a little example here where select equals minus and then civ war int war. So going back to this, if I had changed this command, so this creates dem.wealth with 3 variables. Suppose I come in here and said minus. Now watch what happens to dem.rights, or I'm sorry, dem.wealth. Now it's got 5 variables. And if I do the names on what those variables are, it's all the variables except country, democracy, and GNP cats. You might not use that often, but it's something to keep in mind. Okay, that's it for this introduction to R. Next time, in the next video, what we'll do is we'll start to get into a little more of descriptive, using R to produce descriptive statistics. Repeating some of the same things we've talked about this time, but in a more substantive context. We'll do some basic line plots, following up on the earlier plot we did with carbon and carbon emissions in year, but in a little more political context and hopefully in a way that cements these lessons. So I'll see you next time.